So let's welcome to our next speaker then. So yeah, our next speaker is Chen Huang. He's a professor at the Purdue University. He has done a lot of amazing works using atomic gases to study quantum material and many-body physics. And he also did fantastic work trying to interface atomic gases with nanophotonic cavities, which is my personal favorite. Do we have our slides up? Okay, there. Oh. Okay, so it's not connected. Did you share via Zoom or? Ah, great. Okay, so yeah, let's welcome Chen Lo again.
Thank you very much for the introduction, and also thank you for the organizers for inviting me to give this come to this very wonderful workshop. I'm going to talk about kind of quite concentrated effort trying to couple co-atoms to integrated nanophotonics. And at first it may kind of sounds like a little bit crazy, like why do you want to put co-atoms on nanophotonic circuits? It's kind of a one of the kind of a dream triggered by Jack Kimball when I was still a postdoc with him. And so one of the big motivation of this project is to see whether we can use a highly confined, high quality resonator to increase atom photon coupling, and then use it, to couple an array of atoms, and then use it to mediate interaction between the atoms in principle for quantum summations. But along the road, we actually discovered that actually to really trap a lot of atoms on nanophotonics turns out to be a quite challenging project. But at the same time, we learned a lot of things about kind of how to cooling on this, in particular, two-dimensional planar circuits. And also, there could be new surprises coming from this kind of systems. So since...
So people on Zoom cannot see the slides.
Oh.
Are you sharing on Zoom?
I'm not. I may not have. I thought that this would directly go to Zoom.
Is this not on the Zoom call?
My computer is not, but
was that the previous one as well?
No, the previous one.
I see. It's a Chen Long problem.
Oh, it's my problem. So how do we do it? Share?
Share maybe?
Is it
Can
sharing?
they see it? Can they see it now?
Yes.
Okay. So maybe it's just
That was weird.
just one click. Okay. All right. So I would just start talking about the cavity. So our cavity is basically the simplest cavity you can think of on the integrated photonics. It's just a micro resonator. It's a waveguide that's bent back to itself. It supports the so-called whispering carrier mode resonator, as long as you have resonances, as long as the resonator length fit in individual multiples of the wavelengths. And so and people have been, constantly been able to make this kind of ultra high quality, like hundreds of millions of quality factor. But most of these micro rings have been fabricated using a pretty large curvature, large size. At the same time, they are kind of cladded with glass, right? But for us to couple two atoms, we actually have to unclad them. We have to expose the waveguides to the vacuum. So this becomes a little bit more challenging. So what makes this microring cavity a little bit crazy for coupling to atom is that, well, it becomes a little bit challenging to make a quality factor bigger than 10 million. And we want to shrink the size of the ring such that our cavity is as small as possible, such that we can have large, small volume and large atom photon coupling. So we kind of limit our radius to be about 15 micron. And this gives us a circumference about 100 micron and a more area about 5 micron square. So that's what we have. And the expected photon coupling rate would be about 200 megahertz. If we can actually trap a single atom about 100 nanometer above the surface of the waveguide. And this would correspond to a cooperativity about 500 and with the quality factor 10 million. Another very interesting aspect about nanophotonics is that these atoms are coupled to efficient wave modes. And so outside this vacuum, you have this imaginary part of the wave vector component. And we all know that the Maxwell's equation detects transversality, like K dot E equals 0. And if you have a purely imaginary wave component, that means that you have to develop another component that's along the ratio actual component that's pi over 2 out of phase relative to a main polarization component. And the amplitude are also almost equal. And so that means that necessarily the light that's propagating along the waveguide has to be circularly polarized. And this circular polarization is actually locked to the propagation direction of the wave. And so this gives rise to a very interesting property called chiral optics when we couple a spinball atom on this resonator. For example, if we have a lambda type of level structure, the light that comes in, interact with the atom, can actually flip the spin state, at the same time reflect the light. So they can actually create a so-called atom photon swap gate. On the other hand, if you have a kind of a inverted V structure, one state will couple to light, the other state will not. And so you could introduce non-reciprocity. You can block light along one direction, but not block light along the other direction. This would become a quantum isolator. But for the kind of rest part of this talk, we just think about, we polarize atom in the stretch state, and then we just think of this as a simple two-level structure. We just have a sigma plus transition driving this sigma plus transition. Okay. So in order to laser cool atom onto the surface of this chip, this is a silicon circuit, and then our micro resonator, which is made with the silicon nitride, is fabricated on this chip. In order to be able to laser cool atoms on there, we kind of have to release the substrate, make the substrate completely transparent, so we can send laser light through for cooling and trapping. So to do this, we actually release all the silicon substrate, and then the microring sitting on top of a silicon dioxide versus a silicon nitride at the bottom layer. So to make it tensile straight. So this is a completely flat membrane. And so that could make all this microring stable. And we can make as many resonators as we want and have them commonly coupled to a bus waveguide. And then this bus waveguide then would edge couple to clip fibers. We kind of insist on doing clip fibers because it will give us pretty stable coupling efficiency. And also we developed also grayscale lithography to make a three-dimensional taper up coupler, so you can actually automatically match the fiber mode into the waveguide mode. And we can realize, experimentally realize about 85% coupling efficiency, simulated is about 89%, and this is pretty broadband. And so I just told you that we would want to make a 10 million quality factor, but this is kind of for a lot of experiments that I'm going to show you. We are still working on just the kind of our first generation of chips, like the same chip have been used for 2 to 3 years. And so the quality factor is about 200,000. Right now, kind of gradually pushing toward a million, but that hasn't been updated yet. So these rings are kind of thermally locked to atomic resonance. But in principle, we can also, pattern kind of MEMS devices that we can actually adjust the resonances pretty quickly. So if you think about, so far, if you think about coupling one atom is crazy, then I would say that actually there are some physics that you can make coupling many atoms to micro resonator even insane. And so this is one thing that's called selective collective emission dynamics, and which is actually kind of discovered by Anna, Jeff, and Derek a few years back. And so what happened is that if you can actually trap arrays of atoms pretty dense with their spacing, array spacing, smaller than half the wavelength in free space, then you can always find modes. You can collectively excite modes that would have wave factors that's beyond the line line. The line line is the kind of the wave number of the resonant wavelength in free space. And so, for example, if I have an array of equally spaced atoms, E smaller than half a wavelength, and I can make them excited with phase relationship plus minus plus minus plus minus, then it will correspond to a K that you can actually not be able to find any phase matching condition for this array of atoms to move into free space. The only way for light to propagate is just continuing through the atom array. And so since there's no way you can, for this excitation to emit in the free space, that also means that there's no way you can couple them from free space. And so the only way to do that is, for example, place them nearby a nanophotonic structure where you have high refracting index and can couple to modes that is beyond the line. And this is called selective radiance because these atom array, they can be phase matched, superradiantly coupled to the selective photonic mode with n-atom enhanced emission coupling. However, they are not able to emit into all other channels. So this is subradiantly coupled to all other channels with primary polynomial suppression or emission. And in some cases, as we will see, you can even achieve exponential suppression with respect to atom number. Okay. So deep down to consider this kind of dynamics instead of the cavity QED or waveguide dynamics that we've been quite familiar with is that you have to think about the photon-mediated interaction between atoms considering all the possible modes. What I'm saying here is that in this master equation, so we can assuming photon dynamics is pretty fast, and then we automatically eliminate all the photonic degrees of freedom, we are left with a system of atoms that could couple to each other through the spin exchange interaction, J, that's mediated by photons, or collective dissipated coupling, where we can kind of think of these interactions they're actually controlled by the Green's function of the environment. So Green's function is basically just how the electric field can propagate from one point to another. And this Green's function actually has two contributions. One is from the cavity or the waveguide of interest. Another one is from the free space, non-guided modes. And so this kind of formalism can be, in principle, be used to describe collective emission or light scattering of ensemble of atoms or array of atoms, and has been occupying a lot of research during the past decade. For example, in free space, people have seen collective lane shift. That's a contribution from the collective coherent interaction in the dense ensemble. Or if you place atoms, a few atoms, nearby a photonic crystal structure, you can actually see the collective atom-atom interaction mediated by the photonic crystal. On the other hand, the kind of selective radiance or subradiant of light emission relative to free space, this is purely contributed by, mostly contributed by the dissipated coupling between the atoms, okay? But for all these kind of systems, you either consider the interaction is dominated by coupling to the free space modes or the non-guided modes, or you can consider interaction dominated just by the photonic crystal. But rarely you have to actually think about both of them, right? And so at this moment, so even for atom, ensemble atom coupled to a cavity, there's not this kind of a, you don't have to have this kind of large worry until you actually place these atoms very close to each other. Okay, and so so the kind of synopsis of this talk is that first I want to talk to you about how we integrate atoms onto this microring platform, and primarily work on more like a traditional cavity QED type of experiment. And I'll talk about how we trap a lot of atoms, ensemble atoms on the surface, observe subradiance, and even selective collision emission. And then I would talk about the prospect of this kind of platform to actually realize selective selective radiance with atom arrays. Okay, and so for some of you who may not know actually how cold atom would with integrated circuits, so basically you can actually laser cool atoms on anywhere as long as you can set balanced radiation pressure, light. So in this particular case, we start with cold atoms in the vacuum and then transport it on top of the window. And we can typically collect about 100,000 atoms on the chip, which is, ranges from 0 distance to about 200 micron away from the surface. In fact, actually, we can send a tightly focused light directly on the surface. We can actually observe a array of atoms being trapped. These are fluorescence images, single shots, okay? And so you may wonder, well, I kind of quite familiar with those kind of optical tweezer trap images where you just have randomly filled sites, right? But how come that these are all filled? The reason is that you are shining light to the surface. So there's actually reflection on the surface. So actually form interference pattern. So it actually form an optical lattice. So atoms can be loaded in any of these sites, okay? But the actually loading rate is quite low for the one that's closer to the surface because it's very hard to find balanced radiation pressure near the surface of the resonator. So in this paper, we also talk about, okay, but you know, since this is optical lattice, that's great because you can actually trap many atoms in your lattices, and then you can send a counterpropagating light and then detune the frequency, make it an optical conveyor belt. You can transport atoms onto the surface. And we study a little bit of this, not actually coupling light to these atoms, but if you're interested, you can take a look. On the other hand, I'm going to talk about a kind of a guiding and trapping techniques that we have been implemented that's pretty efficient to actually guide a lot of atoms onto the surface. So the idea is actually very simple. You just shine the light from the backside. Okay, so there, once the light going through this glass membrane, it acts in the far field. It acts just like a dipole trap, draw atoms toward the surface. But once you get very, very close, the structure actually creates all these kind of diffraction patterns. It creates a very tight focusing near the top of the surface that's actually geometrically determined by the waveguide you are shining on. So if you look at the transverse, this kind of size of this beam, this kind of can typically go below the diffraction limits. And it acts like an optical funnel that can help us guide atoms down onto the waveguide. Of course, we don't want, if you don't have anything, right? So this is an attractive beam. So atom would just, you know, if there's no Pauling reflection, they would just hit on the surface. And to prevent atoms from hitting the surface, we can actually send a blue detune light directly into the microring resonator, create a very strong repulsive barrier. So with this, we can actually guide many atoms onto the surface. You can see that, for example, this fluorescence image is showing that where the atoms are guiding onto the microring, which is corresponding SAN images here. So how do we see the atom coupling to the microring? So we typically couple light through a Bose waveguide that's tuned to critical coupling. That means that unrest, the external coupling rate into the ring equals to the kind of internal dissipation rate. And so when the light is on resonance, all the light will be drawn into the microring and dissipated. Another way to think about it is that these light that goes in experience round trip, they want to come out, but they have a tight phase shift, so they have complete destructive interference. But once we introduce a single atom coupled to the photons in the ring, it introduces a phase shift, additional phase shift. And then this phase shift allows the light to go through. And so you can think about this as an atom-induced transparency. And so how large this resonant transmission can be depends on single atom cooperativity. On the other hand, if I couple n atoms, well, they would all see this resonant mode in phase. So basically, you can kind of replace the cooperativity, single atom cooperativity, just by the effective number of atoms that couple to the microring times n, where n is just nc is just n times g squared divided by gamma naught. But there's a caveat here. The caveat is that we ignore all other possible collective effects that's due to these atoms coupled by the free space modes. This is something that we will explore later. Anyway, so we're dropping atoms onto the surface. We actually see relative to initially no transmission with no atom, we can actually see up to like 30% of atoms. We don't, why is the transmission low? Well, because we don't always have atoms there. So the average transit time is about 3 microseconds. And so with some modeling and fitting, we determine that the peak floss is about 400 atoms per millisecond. And the peak cooperativity is about 8 with atom photon coupling rate 140, about 130 megahertz. And any given instant of time, we have about 0.7 atoms coupling to the microring. Well, you might wonder, how do you know? right? How do you know it's less than one atom instead of many atoms there? Well, another way to check that is that we do this Henry Bon-Trees measurement to look at the coincident counts from the 2 ports of PBS, BS, beam splitter. We can indeed see single photon blockade by post-selecting all these atom transiting events. And so by fitting to a model, we actually can determine that in the case where we do not have an optical barrier, we can reach peak average cooperativity 8. If there's a barrier, the average cooperativity is about 3. And another thing is that this thing doesn't really dip below, dip all the way to 0 is because we always have finite leakage background, because we basically rely on the microring, bare microring to block the rest of the photon from being transmitted. So there's always a little bit of background. So in some sense, this is kind of an integrated version of the classic microtorr experiment done by Kimball Group at Caltech. And we could, in this kind of dropping thing, we can have a few milliseconds of pretty good single photons coming out. And we can identify more than hundreds of atoms transit per drop, right? Well, this is just single atom. Well, I want to talk about trapping a lot of atoms because that's really what I wanted to do. But how do we do that, right? So I already told you we actually need balanced radiation pressure to laser cool atoms. Unfortunately, on this kind of integrated circuit, it's very difficult to balance it. But how do we achieve that? We no longer can use traditional kind of Doppler or polarization gradient cooling methods. Well, but it turns out that there's some magic in our barrier here. I already told you that these lights that's traveling on the microring, they are circularly polarized. And so is the barrier. So what it does is that this circularly polarized light that not only creates a repulsive potential, it also effectively creates a fictitious magnetic field, like a magnetic field. And this magnetic field is on the order of tens of milligauss near the center of the trap, which is around 315 nanometer. It's a very gentle trap, 3 nanometer above the surface, and then have very strong gradient, vertically and then horizontally. So what this then would lead to is that the atoms acquire spin motion coupling in this kind of trap. And if you have spin motion coupling, then we can apply a trick, just do optical pumping. So we just send a sigma plus polarized light, try to pump atoms to a state where polarized state, which at the same time should be a dark state. Then by doing that, we can basically cool the spin degrees of freedom while this potential mix the spin and motional degrees of freedom. Okay, so this is kind of a very layman's way to explain it, but there's a little bit details on it. Then this entire technique is based on degenerate monocyclic cooling. Okay, and just by applying, so do nothing, you just have the atom drop down and then apply optical pumping beam. We can go from seeing a few millisecond atom signal to hundreds of, at least 150 millisecond single atom lifetime of transmission. If we apply continuous optical pumping to cool the atom, we can have the signal roughly around 700 milliseconds. This is almost close to vacuum lifetime limited performance. So we can actually characterize the temperature of the atoms. That's as low as 20 microkelvin. Density is very high, it's 10 to the 13% in the cube. And it's so high that, in fact, so we are actually using cesium atoms. If we put this, when we perform the experiment, put them into the absolute lowest energy state. But if we put it into another state, you start to see an inelastic collision between atoms. So the lifetime becomes immediately short. And so just to kind of quickly say that, how do we measure the temperature? We can actually lower down the barrier. We can see that once the barrier is lower than the initial trap depth, then we can actually start to see atoms leaking out. We can actually characterize how fast they leak out versus the barrier height. And this is how we actually characterize the temperature. And by using this method, we can also control the number of atoms inside the trap. We can see by reducing atom number, the transmission peak becomes narrower. And also the single atom decay following a fast excitation sorry, not single atom decay. The fluorescent decay following fast excitation is slowing until it approaches single atom decay rate. So all of these kind of as a signature that we have seen observed super radiant coupling of these atoms to the microring. And by getting this n atom cooperativity divided by the expected single atom cooperativity, which we can evaluate by knowing the trap distribution, we have up to 17 atoms in the trap. Okay. Now coming into this, the property of this dense ensemble trap on a microring. So their distribution transpose is actually pretty narrow, about 200 nanometer, vertically 0.5 micron, and then 4 micron along this along the waveguide, microring waveguide. So that means that we actually have up to 100 atoms, on the order of 100 atoms in the very small volume. Okay. So when we actually send resonant light through this ring, we are exciting them. Like, for example, if we send a pulse, we can create a kind of phased excitation where this wave factor is actually almost 2 times bigger than the free space wave number, because the refracting index of this microring is about 1.7. So that means that these atoms are excited, fast mismatched to the free space modes. Presumably, they should not decay into free space. Well, we got very excited. We started to talk to our friends. One of them is Chen, IFO, and then so you mentioned that actually a similar experiment done by free space sample was done in 2023, reported in this PIL. So what they do is another very beautiful experiment is that they first excite a time decay state using free space power, and then they very quickly so put one excitation in the cloud, and very quickly apply another 2 pi pulse to drive a round trip using another state. So they can imprint another phase. And the sum of these 2 phases get you a wave factor that's beyond the line, okay? And then they monitor the subsequent decay dynamics. And what they saw is actually that no matter how they tune, the decay was always either close or slightly bigger than single atom decay rate. And this turns out to be quite surprising, but if you think about it, right? So you are having a dense atomic ensemble, and then sometimes they get very close. And then when they excite them, they not only have dissipative coupling, they would also have coherent coupling. When those atoms are very close, those coherent coupling actually is going to kill your phase coherence. And so a time decay state doesn't respect that dipole-dipole interaction coherent part. And those part will very quickly dephase your any time decay state that you create, and then eventually it will lead to single atom decay. Right. That's kind of a very simple argument of it. Well, it's a little bit kind of disappointing, but we think that, okay, well, we don't have to limit ourselves to just time decay state, because we don't need to do multiple pulses, right? So how about let's try something else? For example, let's try steady state. We drive the states for long enough time and then turn on the light. Well, now steady state, they would respect the dipole-dipole interaction because they are being driven into a state that has to respect both of the parts, coherent and the dissipative parts, right? And so that's what we were trying to do and try to model it first. Well, to give you a little bit more details about this. So for the cavity, because we are running a cavity on resonance, it only has a pure dissipative contribution. So all the coherent effect is actually coming from the free space interaction, okay? And since these atoms are placed very close to a complex dielectric stacks, right? We need to make sure that we know how to model them. Well, luckily and unluckily, our atoms actually trap pretty far away from the surface. So we actually resorted to kind of numerical calculation to see whether the Green's function is really something different than the free space. It turns out that it's actually pretty close to the free space model. So that makes the modeling very simple. We can use completely just kind of analytical model using the free space Green function plus the non-cavity Green function to model these entire dynamics. And so from the calculation, basically, we can calculate total photon emission rate. But we know that these atoms, they would need to couple to primarily two major channels. One is the photonic channel, basically the cavity mode. The other one is all other non-guided modes. In our experiment, we do not go out to a lot of detectors around. Well, a lot of experiments, they only put one detector in your photonic channel. Now, here the question is that for this kind of system, they can have different collected emission behaviors. Would this detector, just one single detector, be enough to understand the kind of decay behavior? So this is also what we try to study. Okay, so it turns out that for the decay through the photonic channel, the coupling emission rate to the photonic channel in the steady state and the time decay state, you can actually see that for a short time, they all decay pretty fast relative to the single atom decay, which is kind of a dashed line here. On the other hand, if you look at the decay emission into the non-guiding mode, steady state primarily is actually pretty subradiant, meaning that it's slower than single atom decay. On the other hand, time decay state is kind of still fast. That's kind of consistent with the study done by Iqbal and also the Fudan group. And the fact that we can actually use two different kind of driving, we can actually see this very different coupling to the two different modes, actually suggests that we can actually potentially see this kind of selective emission behavior, right? And so we just go on, we just go on to look at this. We turn on the excitation and then turn off the excitation. For the case of TDS, we just use a short pulse, roughly 6 nanoseconds, faster than other time dynamics. Another one, steady state, we just use a much longer pulse. And then we turn off the pulse and then look at how signal decays. Remember, we only measure the emission to the photonic channel. And then typically we just very naively just fit the exponential decay. So what we actually know is the rate of change of RC divided by R, a rate of change of R. We don't actually measure the photon emission rate because of, again, difficulty in experiment. You have to calibrate this, calibrate that, right? But most of us, we're just measuring the rate of change of photon emission rate. Is this sufficient? Well, let's see whether we can see this kind of a behavior or not, right? So how do we get from rate of change of the coupling rate to the photonic channel to understand some behavior of coupling into the free space? One of the things that we think of is how about we just continue to excite the gas through the photonic channel, but we kind of keep pushing the atom further away from the waveguide surface until the case where the NC1, the coupling to the waveguide, is no longer dominant. It's much smaller than coupling to the free space. In that case, maybe in the case of C1 goes to 0, maybe we can extract some information about decay into free space, right? So we do this, right? We study the steady state and time decay state by gradually tune the C1 to 0. And then it turns out it's quite linear. We can actually perform a fit, extrapolate it to the limit where C1 goes to 0. And quite surprisingly, no matter how we tune the atom number, steady state kind of all crosses near 1. Time decay state is crossing somewhere above 1. Okay, and even increases when we have more atom number. This is kind of surprising, but if you actually look at the kind of expected dynamics from theory, it is not that surprising. The reason is, well, if you kind of empirically define this kind of a total emission rate, decay rate as this, then you will have components, contributions from cavity and contributions from free space. What we measure is never actually this. It's different by a factor theta. Theta is the ratio between the rate of change of cavity photon decay rate versus the free space photon decay rate. Okay. And if your system is not decaying singly exponentially, then this will not equal. So whatever we measure by tuning this to 0 will not give us gamma F, but just gamma theta. And in fact, if you actually try to calculate this theta factor, you see that for steady state, this number always bigger than 1. So photon emission into photonic channel decays faster than emission into free space. It's opposite for time decay states, right? So what we measure turns out for steady state to be the upper bound of the total photon decay rate, and the time decay state to be the lower bound. It's kind of weird. Okay. So if we try to look at the intersect, so when we tune the coupling to the cavity completely to 0 as a function of atom, for steady state it's surprisingly flat. There's no change, but for time decay state it's kind of going up. However, it's kind of this number is kind of going up much faster, and this is something that we are still trying to figure out. We don't quite know yet why there's this discrepancy. Maybe the actual number of atoms is actually much larger than we thought. But if we take this measurement and divide it by the calculated theta factor, we immediately see that for steady state, the decay of emission into photon into free space is going down, and then going into for steady state, and then going up for time decay state. On the other hand, we can also extract the coupling, the decay to the cavity. It turns out that it doesn't matter whether it's time decay state or whether it's steady state. It's always linearly proportional to NC1. So it's Sporadian coupling. So this is kind of consistent with theory expectation. Both steady state and time decay state show superradiant emission to the resonator. However, emission into free space for steady state is subradiant, but time decay state turns out to be superradiant. Okay, and so this is for ensemble dynamics. I would say that without our measurement, actually we're measuring average properties. So we see that kind of a thing. But how about if we can realize this in the fixed atom or even better, atom array? In this case, right, so every time we drive, we can excite always the same state, and then we can measure the property of that state. This can be realized using the so-called two-color evanescent field trap. We just send blue and red to tune light. We can actually form a pretty tight trap minimum near the surface, and we can even form an optical lattice along the waveguide, which is a lattice spacing below half of the wavelength. We can tune the position of the trap all the way below 100 nanometer, if we can realize it. So from prediction, so we can excite with K waveguide that's about 1.7 times the free space value. And then with this, the suppression for the decay into free space will be very, very significant. In the case where we have a linear atom array, with just a few tens of atoms, it could suppress polynomially down to 2 orders of magnitude. If we can actually have a ring-shaped atom trap using, for example, a ring resonator, then there's no edge in this array. And so light no longer can escape, right? And in this case, the decay goes unlimited. Of course, we have not considered any finite wave packet spreading. So that could introduce additional defacing mechanism. In this particular case, the atom array, since we are exciting primarily just one state, actually they would decay single exponentially with theta about 1. So we would expect that this thing would continue to go below when we measure this RC over R over RC. It will continue to go all the way to 0, both for steady state and time decay state. So with this, I give a very quick summary. We demonstrated superradiant coupling and trap atoms, and also demonstrated kind of selected collected emission with a cavity-driven ensemble. Of course, to really move towards the real quasi cavity, we better be able to trap atom closer to the surface. This can be realized using a decent wave field trap. And then with fabrication improvement, we can talk a lot about this. I completely skip it. But we expect that we should be able to achieve cooperativity bigger than 50 with quality factor median. And since we have demonstrated a laser cooling technique to high phase space density, in principle, one may actually create order array, maybe even by reaching quantum degeneracy, for example, making the mines in there. Okay, and of course, with that, it's highly likely that selective radiance can be achieved. So in the last slide, I kind of show you the system, the vacuum chamber with a lot of optics, but actually this is kind of a 3 years old photo. It's actually filled with a lot of other optics. But kind of imagine, so we kind of want to currently working on upgrading to a glass cell system with microscope objectives looking at both sides of the circuit. So in this case, we can, in principle, use this kind of back illuminating method to create microtrap arrays and trapping many atoms using Raman-Simon cooling methods. And one of the kind of the possible exploration, is to go to, even two-dimensional, more complicated circuits like two-dimensional photonic crystal, creating band structures for the photons, and maybe create the directional coupling, directional emission, or even give these photonic crystal topological property with atom integrated, right? Last, I was actually very excited to hear that you can actually make circular polarized light with dynamical control. That means that one can actually make all this light launch out from the photonic circuit, and those are the necessary lights for laser cooling atoms on the surface. And it turns out that all since we actually have a large window, actually we can have all these lights crossing above the window, and then we can laser cool atoms directly on. So this might provide, in principle, potential future route to actually miniaturize coatom circuits, into really just a pocket size, right? So with this, I would like to kind of acknowledge the group contribution. So a lot of experiments are done by my postdoc, Xin-Chao Zhou, who's currently at Niels Bohr Institute. And fabrication is done by Zhihan, who's currently working with Sunil Bhavi, who's also a lot of this kind of edge bar thing. And so we are actually collaborating to implement piezo MEMS tuning on the circuit so that we can actually very quickly modulate this microwave resonances. So these are the current group members, and thank you for your attention. Thank you.
Thanks, Chen. We have time for questions.
Thank you for the nice talk. Early on, you showed that you could have multiple of these ring resonators connected to a single waveguide. So I'm wondering, what are the practicalities of using more than just one of these, and if you can maybe explore some waveguide QED physics or something like that.
Yeah, of course. So you are saying these with multiple resonator couple or just the waveguide? Multiple resonators. Yeah, sure. So that would be implemented when we can actually have control array that is guiding. And so that's why having realized this is very important. So currently we can only check one given
Yeah, hi. For your coupling to the ring cavity, ultimately it will be important to have very little standing wave component, right? To have a homogeneous coupling along. Or do you see any signs of a standing wave forming, or do you have a limit on how much backscattering you have in your ring cavity?
So currently, if you look at the transmission spectrum, the degree of backscattering is so for this particular case, this is pretty much single peak. So, but when you start to see this start to bend up, that's when you start cascading. And at this moment, we align the atom polarization axis such that it only couple to one direction. So if there's cascading, we just treat it as loss. So that's actually contributed to a little bit more reduction of the quality factor. But in the end, if there's actually very significant backscattering, for example, there's a very strong mode mix, so then this mode becomes standing. So that's what you are referring to. Then in this case, then we actually have to do the alignment. So
So we have to make sure that these atoms are aligned to these peaks to maximize the power.
Thank you for a nice talk. You talk about how the time decay state and the steady state have different free space emission properties. Can you tell us more about how you did the experiment and intuition why it affects a free space emission property?
So in terms of experiments, the only difference is just how long we excite the atom. So for the steady state, we typically, as you can see, the pulse width is a few times the signal amplitude. So that would be sufficient to drive the system into the state. Also, because these atoms are already at optimal temperature, so within the few tens of nanoseconds, they're able to move by a couple of minutes. So they can be considered station. And so this is the way, like a long house way to drive steady state. And for time decay state, what we do is show power, but we don't have infinite short. We have like 6 nanoseconds. So we also make sure we evolve our calculation according to the power shape to make sure that it's close to the time decay state possible. And so what's the difference between steady state and time decay state? The key difference is the following. So if you are exciting a time decay state, then first you will imprint your face on the example. Second is that how strong that atom is.
Babe, I'm gonna take an Uber. Yeah, because it's not gonna be cheaper or faster tomorrow.
So in the case of time decay state, we completely ignore the superunit interaction. And this satisfies the expectation that they would emit back into the microunit and add. But since there's actually while actually shallow out, there's actually dipole interaction coming from the free state. And that would actually create this kind of state. And so in the end, on the other hand, for the steady state, what I can say is that every atomic configuration, it actually has some eigenmode that it will form subradiant state, subradiant configuration. And so, let me give you one example. This is kind of a random distribution, but this is kind of a spectrum. We try to help for a given random distribution, what would be the kind of a possible transmission spectrum. All these very narrow ones, they are actually subradiant. But of course, each of the realization is so we do not necessarily decide all this stuff. So we kind of sometimes like that, sometimes we like the other one. So we would end up with for the time state, most of the we have a distribution, and for the space, and we will also have a distribution for the
Thank you.